Okay, guys, can you hear me or not? Can you? Okay, okay. Thank you. Thank you for confirming. Okay. So, and I'm assuming you can also see my slides, right? So, last time we started talking about, okay. So last time we started talking about the topic of Endianness, right? And but we were in middle of that topic and we had to stop there. So we will start today from the same point. And other than that, we will be covering assembler directives, some more assembler directives, and we will also be covering the addressing modes, right? So what is addressing more what is the Indianness. Again, let me give you the same example. Suppose you have this 16-bit data, where 2A is your least significant byte, and F4 is your most significant byte. And let's say that you have these memory locations which are, let's say, initially empty. So the addresses of these memory locations are 0 to 9, right? And our job is like, what we want to do is that we want to place the data, the 16-bit data into, is it 16-bit? Yeah, this 16-bit data into, actually it's not 16-bit, it is uh 8, 16 and 304, it is 32-bit. So we want to place this 32-bit data, or let's say the 4-byte data, into the memory, right? Uh, so the question is that how we can place this data in the memory. So the one option is that we can start placing the data in the memory starting from the least significant byte, right? So and this approach of placing the data starting from the least significant byte is known as little endian, right? So the so here is an example. Like, for example, if we are starting at address 2 in the memory and we start putting the data in the memory starting from this address, then 2A will go to the memory location at address 2. The next byte, 04, will go to the memory location 3, and CD at location 4, and F4 at location 5. So most significant byte goes to the highest address, and the least significant byte 2A goes to the lowest address or the starting address, right? So this is known as the little endian. The other approach is the other option to answer the same question is that we can start placing the data. We can start by placing most significant byte of the data at the starting address, or let's say the lower address, right? So which means that we start writing first the most significant byte, then the next one, then the next one, and then so on up to until we reach the least significant byte. So if we use that approach, which is known as big endian, then this is how our memory will look like. So at address we will have F4, right, which is most significant byte. Then at address 3 we will have the next byte, less significant byte, CD. And then at address 4 we'll have byte 04, and at address 5 we will have the least significant byte 2A. So the difference is that in least significant byte, your sorry, in little endian approach, your least significant byte goes to the lowest address or the starting address, while in the big endian approach, your most significant byte goes to the smallest address or lowest address. Okay. So little Indian approach, this is used by some microcontrollers and processors like Intel x86, x8064, and Atmel AVR microcontrollers. So which mean that our microcontroller, which we are using in lab or in this course, it uses the little Indian approach. So it starts putting data in the memory from the least significant byte, right? And big Indian approach, this is used by also some other devices like Motorola 6800 or 68K. So here is an example. Suppose that we want to read 4 bytes from memory starting at address. So this is the current situation of the memory. So it already contains the data, right? And we want to read this data, let's say 4 bytes, and want to put it in a register, right? So the if we want to put it in a register, then using little Indian approach or little Indian placement, what will be that value of that data, right? So any questions before we go to the quiz or the poll? Okay, so if not, then yeah, I'm launching this quiz. Yeah. No, 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 I think this is not correct one. Let me go back. Uh, 14. Let me try this one then. Yeah. Okay. Why I cannot launch it? It shows that timer is not started. Let me try again. Week 10, day 1, quiz 14. I don't see an. Okay. Yeah, now let me go back and wait a minute. It was week 10, day 1, quiz 14. It's a mess. Yeah. Okay. Now please go ahead and attempt this quiz. Okay. So when you remember, this is like we are going to read the data from memory using little endian approach, right? So if you read the data using little endian approach, it's mean the address, the data at the first byte location or the first address is the least significant byte, right? So the data we are reading from first location is two ways, so it makes the least significant byte, then the next one makes the next byte 04. After that, the value at 4, address 4 is the next byte, and the value at the last address 5 makes the most significant byte F4, right? If you have any questions, please ask, okay? Another example, uh, actually, we have the same content of the memory, and we again want to read 4 bytes of the data from the memory, but this time, and again starting at address 2, but this time we are assuming that we are going to read the data using big Endian approach, right? So if we want to read 4 byte of data using big Endian approach starting at address 2, what will be the value of that data? So again, let me release the uh, poll. So if the older one was 14, this should be 15, right? Yeah. Okay, go ahead. Okay, I will take your question after ending the poll. Okay. So let me explain the answer and then I will take your question. So again, we are using the big Indian, right? So if we are using the big Indian, remember the starting address or the lowest address holds the most significant byte, right? So which is 2A here, right? And the higher, and then the next byte contains the next byte or two when we move towards the least significant side, right? 04. And then the next address 4 holds CD, and then the last address contains F4. So F4 is the most significant byte, right? Now, if you compare these two things, if you like look at the content of the memory in two examples, it is same, but the actual value of that content, it depends upon how you are reading the content from the memory or how you are writing the content to the memory. Are you using little Indian approach or big Indian approach? Because if you are using the little Indian approach, the first byte at the starting address is the least significant byte. But if you use the big Indian approach, the first byte at the starting address is the most significant byte, and it totally changes the meaning or the value of the data. Okay. So now let me check your text messages. Uh, okay. What is choice one and choice two? Okay, the answer choices are choice one. Okay, sorry. I think I made a mistake while making that poll. But anyway, I think you guys got that you understand the example, right? If you are not clear about how we are reading Little Indian or data and Big Indian data, let me know. But otherwise, you are correct. There was a problem or mistake in the poll or quiz itself. Do you have any question related to Little Indian, Big Indian approach of reading, writing data? If yes, let me know. Otherwise, I'm moving to the next slide. Okay. So in upcoming slides, we are going to cover some assembler directives. So remember, what are directives, assembler directives? Assembler directives are the instructions for the assembler program. They are not instructions, right? Directives are not instructions. They are not executed by your hardware. You are just telling your assembler to do something, right? So remember, what other directives we have covered earlier? We have covered the directive like equate, EQU, right? And we have covered like global, and we have covered common, we have covered dot text, we have covered dot data, right? So all of those directives, they were conveying some information to the assembler. They are not translated into the instructions, and as a result, they are not executed by your hardware, right? So similarly, there are some other directives which you can use within your instructions. So for example, when you say load immediate, remember until now what we have been doing. We have been doing like load immediate R20 and then putting some value here, right? For example, let's say 10, right? So you are saying put value of 10 into R20. But instead of writing immediate value 10, you can also put an expression here, right? So for example, and in that expression, you can use you can make any expression which uses these operations like plus, minus, multiply, and division, right? So for example, if you say 5 plus 3, so what does the assembler will do? It will first assembler will add 5 and 3 and it becomes 8, and actually the actual instruction that will be executed by your microcontroller will be load immediate R20 comma 8, right? So assembler will replace 5 plus 3 with 8, right? Similarly, if you say load immediate R39 minus 3, so assembler will compute this expression, not your microcontroller. So when it computes this expression 9 minus 3, it becomes 6. So it replaces your this instruction in the assembly in your program with LDI R30 comma 6. And then that instruction will be executed by your microcontroller. Same is the case here. 5 times 7, so it will be replaced with 35, and 8 by 2, so it will be replaced by 4, right? So these are you can use an expression which as a second operand in your load I instruction or anywhere where you are allowed to use the immediate operand, like for example in add immediate or and immediate or immediate, right? Or subtract immediate. Similarly, there are also in the expression which you are using with the immediate operands, you can also use other operations, logical operations as well. So, for example, AND operation or exclusive OR and NOT or complement, right? But this is bitwise AND operation. Bitwise mean, like for example, here when you are saying 0x50 and 0x10, so what will happen? That first you will do, I'm not writing 0x, but it is understood that the values are in uh, hexadecimal form. So what will be the AND operation? So when you do AND of 0 and 0, it will be 0. And what is binary of 5? So binary of 5 is 0, 1, 4-bit binary of 5, 0, 1, 0, 1, right? And binary of 1 is 0, 0, 0, 1. So when you do AND, you will get 1, 0, 0, 0, which in hex form is 1. So what will happen is that first this expression will be computed, this one, and it will result into the bitwise AND of 0x50 and 0x10, which is 0x10 here. So your assembler will actually execute this instruction here, right? Not assembler, your hardware, right? So assembler will simply replace this instruction with its equivalent form by first computing the expression itself, right? Same is the true for the expression involving a OR operation. So here first the OR operation will be performed between 0x50 and 0x10, which is equal to 0x51. So assembler will replace this one with its equivalent form here, and then this form will be executed by your hardware or the microcontroller. And same goes for exclusive OR and NOT operation. But remember, all of these AND, OR, exclusive OR, and NOT, these are bitwise operation, which mean that the corresponding bits of two operands, they are ORed or ANDed or exclusive ORed with each other. Any questions here? Okay, and there are also other directives which are shift operational directives, which you can also use when you are wherever you are allowed to put an immediate number. So, and again, in an expression, you can combine all of them. For example, you can have an expression in place of immediate number, and that expression can possibly have, let's say, all of them, like plus operation, addition operation, subtraction, multiplication, division, and or exclusive or not, shift left and shift right, all of them, right? So by assembler, what the assembler will do, assembler will get the overall result and then replace it with the equivalent instruction. Okay. So yeah, let me discard these annotations so that I can explain this shift left and shift right thing. So uh, this shift left operation, actually, I explained it last time, where in our example we were using the shift left operation. So here basically you are saying that shift left the binary of 10 one time, right? And if you remember, when we were discussing arithmetic instructions, we said that when you do the shift left one time on a number, it is equivalent of multiplying that number with 2, right? So 0x10, let me convert it into binary form. So it will be equal to 0, 0, 0, 0, and not 0, sorry. Can I undo? It doesn't allow me to undo. So let me again. Yeah. So 0, 0, 0, 1, and then 4 zeros, right? So this is binary of 0x10. And then I'm saying shift this number towards left, right? Towards left. How many times? One time. So when I shift this one time, what will happen? That all the bits, they will move towards shift. So the most significant bit will be like discarded. So I will have 0, 0, 1, 0, and four zeros. From the rightmost side, you will start filling it with zero. If you remember how things work in the logical shift operation, right? So this is equivalent to what? This is equivalent of 0x 2 0, right? So actually, so assembler will replace it with 0x20, and then this instruction will be executed, right? And again, as I said, when you shift left a number, it is same as you are multiplying it with 2. So it was 0x10. After shifting left, it becomes 0x20, which means it is multiplied with 2. Okay. Shift right operation. So it performs exactly the same thing, but just in the opposite direction, right? So here you are saying 0x8 shifted 2 times toward right direction. So I am not going to write the 8-bit binary. I'm just writing 4-bit binary. So 4-bit binary of 4-bit binary of 8 is 1000. If I shift it right 2 times, so it will become 0 0 1 0, which is equal to 2, right? So assembler will first compute that expression, replace it with the result of the computation 0x2, and then it will your microcontroller will actually execute this instruction, load immediate R16 0x2. Your microcontroller will not, its microcontroller is not going to perform this shift right operation. Your microcontroller will not. Assembler will first perform this operation on your host machine, which is, let's say, your Apple laptop, and replace it with 0x2, and then send this instruction, load immediate R16 comma 0x2 to the microcontroller when you will load that program on the Arduino board. Okay. Any questions here? No? Okay. Okay, there are two more directives, high and low bytes. So using high byte, you can get the high byte of let's say uh, 2 byte number. So for example, 0x1234 is a 2 byte number. So when you say high, it will give you actually 12, right? And when you say low byte, so it gives you the low byte, which is 34 in this case, right? So when you are writing, for example, load immediate, uh, low 0x1234 and R20. So you are basically you are saying that my data has 2 bytes. One is low byte and the other is the high byte. So these two instructions are equivalent of saying this one, load 34 into R20 and load 12 into R21, because 12 is the high byte of the operand 0x1234, and 34 is the low byte of operand 0x1234. Another example, let's say if you write low minus 200, load it into the R20, and load high of minus 200 into R21. So you can first simply convert it to minus 200. You can convert it into the how to say, 2's complement form, right? Which is equal to double F38, right? So the low byte is 38, high byte is FF. So it is equivalent of saying load 38 into 20, because 38 is the low byte, right? And load FF into R21. Any questions? No? Okay, then let's go to the poll then. Week 10. Okay, this one. Okay, go ahead and attempt this one. Okay, so the correct answer is the last one, right? Load immediate R16, comma low 0xFF0 and load immediate R17, comma high 0xFF00, right? Uh, some students have selected the third option, which is load immediate R16, comma R17, comma 0xFF0, which is not correct because load immediate instruction, it takes only two operand and one of that is register, destination register, and the other is the immediate number, right? So, by the way, when you let's say if you accidentally select a wrong answer, does the poll allow you to attempt the quiz again or not? Like, can you change your options after selecting one time, first time? Can anyone respond to my query? Okay, I haven't tried. No. Okay, it doesn't allow you, I guess. Okay, 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 okay. Uh, okay, so any questions before we move to the other next topic of addressing modes? Okay. So addressing modes. Before we discuss various addressing modes supported in the AVR microcontroller, we first need to know what the addressing mode actually it is. It is basically a mechanism which is used by the instructions to specify where the to specify how to access the operand which is used in an instruction, right? So, like where the operand is it in a register? Is it in memory? Is it part of the instruction itself? If it is in memory, how to access it? Do you specify the address of the location where it is, or do you specify it as a pointer and so on and so forth, right? So basically, addressing mode it tells an instruction how to get an operand or from where to get an operand, right? So there are 13 distinct addressing modes in AVR microcontroller, and they are grouped into six different categories. Single register mode or immediate register addressing mode, direct addressing mode, register indirect, flash direct, and flash indirect. I will try to cover the first four todays, and then the remaining two last two we can cover in the next lecture. Okay. So yeah, my mistake. Why I again use Qs one as a numbering, so it should be Qs2, right? Yeah, yeah. Go ahead and try this one. So while you are doing that, maybe I can quickly fix this thing here. Okay. So the correct answer is that an addressing mode specifies the way of accessing an operand. It does not specify the number of operands in an instruction. That is not the job of the addressing mode. The addressing mode specifies the way of accessing an operand, how the operand will be accessed, right? So let's have a look at single register addressing mode. Uh, in this case, if an instruction uses single register addressing mode, it's mean that operand is in the register itself, and there is only a single operand, and that operand is in a single register, right? So examples are like, for example, increment RD instruction, right? So in this instruction, you have only one operand, and that operand is in the register, right? So for example, so this is just an opcode of the increment instruction. So here these green bits, they are used to specify the destination register, right? So for example, if you say increment R19, the value of this, so the opcode will be the same, it will stay fixed. But these value of the green bits, they will change depending upon your register number. So if it register number is 19, so it will be 1011, which is equal to 19, right? So here basically you are saying that this instruction is saying that I need an operand, and uh, but that operand is in the register itself, right? Similarly, decrement read instruction, it also uses single register addressing mode. Okay, immediate addressing mode. So immediate addressing mode is sorry. Okay, immediate addressing mode. So this mode is used in the instructions which actually allow an immediate operand. For example, load immediate instruction, or subtract immediate instruction, or AND immediate instruction, right? And how the if you look at the opcode of this instruction, so you will have two things. Do you have two operands? Definitely you have an opcode. Other than the opcode, there are two operands. One is the register, and the other one will be the immediate number. The immediate number will be part of the instruction itself, right? It will be part of the instruction code itself. However, these 4 bits of the instruction, they will be used uh, to find to specify the register that will be used by the instruction, and it can be any of the 16 registers, like from 16 to 31, right? So that's why you have 4 bits from register number 16 to 31. So depending upon the value, it will go either to like 16 or 17 or 18 up to 31, right? So only 4 bits to code register index for R16 to R31. So if all zeros R60, R16 will be selected. If 0001, then R17 will be selected. If all ones, then R31 will be selected. Okay. So here is an example of load immediate. So when you are saying load immediate 25 into R19, so what will happen, that these D bits, they will be used, their value will be set equal to 19, right? Because not equal to 19, but a value which will select the 19. So if one is for 17, two is for 18, and three is for 19, right? And then these bits, 8 bits, they will be used to encode 25. Similarly, for subtract, yeah, the opcode is different in between load immediate and sub immediate, right? And again, 4 bits are used to specify the register, and 8 bits to specify the immediate number. Again, and I is another example. So again, opcode is different, but other than that, the format is same. You will have 4 bits to specify the register and 8 bits to specify the immediate number. Okay. Any questions? So here what we are saying, that yes, this instruction needs 2 operands. Actually, not 2 operand. Uh, it needs one operand, but that one operand is a immediate number, and that immediate number is part of the instruction itself, and the destination is specified by your 4 bits, RD bits. Okay, let's go to the quiz then. Okay, go ahead and try it. So actually there can be more than one correct answers. Okay, let me stop here. So for the first question, select instructions that use immediate addressing mode. So there is only one instruction that is using the immediate addressing mode, and that is add immediate R18, comma 10, right? And for the second question, select instructions that use single register addressing mode. So there are three instructions which are using single register instruction mode. Sorry, single register addressing mode, which is, and those instructions are increment R17, negate R18, and decrement R19. Any questions? Okay. The next addressing mode is two register addressing mode. So this is the case. This addressing mode is used in the instructions which have two registers as an operand, right? So for example, add instruction which uses one source operand and another destination operand. Both are added together and the result is put back in the destination register. Another example is sub instruction where uh, source register is subtracted from the destination register and the result is put back in the destination register. And when you will look at the opcode again, before I go back, there is a before I explain that, there is I want to just emphasize something here in context of this figure. So although we are here saying that 4 bits will be used for specifying the register, the location of those 4 bits within the code of the instruction is not here. Here we are showing it looks like that they are the least significant 4 bits, but actually they are not least significant 4 bits. They are the 4 bits like starting from bit index 4 to bit index 7, right? Again, if you see here, bit index 4 to bit index 7, bit index 4 to bit index 7. But this figure basically only emphasize the fact that 4 bits are used to specify the destination RD register or destination register. So, but if you say that you want to infer the location of those bits, then this figure is not correct in context of finding the location of those bits. So for that you need to look at these figures. So just like this figure is just used to emphasize the fact that 4 bits are used to specify the location, but the location of the bit themselves in the within the code of the instruction, for to find that you should look into the opcode of the individual instructions. Same same is here. So here you have like let's say a two register instruction using two register addressing mode. So 5 bits will be used to specify destination registers, and 5 bits will be used in the instruction code to find the source register. So you are just indexing into the general purpose registers from 0 to 31. Okay, the next addressing mode is direct addressing mode, right? So until now, all the addressing modes which we have seen, like single register addressing mode, immediate addressing mode, or two register addressing mode, all of them were getting their data either from the registers, or they were getting the data or the operand as an immediate number. So that operand was embedded in the instruction code itself, right? None of them were capable of reading the data or operand from memory. So direct addressing mode is the first addressing mode which we are going to see that actually allows to read the data from the memory location, right? So the operand data is in RAM, that is in data memory location, whose address is known and specified as part of the instruction, right? So remember, in immediate addressing mode, what we were doing, we were specifying operand as part of the instruction. But in direct addressing mode, we are specifying the memory address of the operand as a part of the instruction. So here is an example. For example, this instruction, load data from the static memory. So here you specify the address, not the data. So this is address of the memory location from where you will read the data, right? So here you are basically saying go to the memory address 0x313, and whatever data is stored there already, read that data and put it in the R19 register, right? Or for example, in store to the static memory, so you are saying that read the sorry, put the data from register R19, for example, in the memory location whose address is 0x95. Okay, so you are specifying address as part of the instruction. So address is the part of the instruction code itself. Just like in immediate addressing mode, the operand itself is the part of the instruction code. So this is how data is accessed. So these instructions are both load LDS and STS. They are 32-bit instructions. So you have opcode, and then you have 5 bits, 16, 17, 18, 19, not 5 bits, 4 bits, 4 bits to specify the register, right? And then the 16 bits available to specify the address of the memory location from where you want to read the data or to where you want to write the data. Any questions? Okay. So next addressing mode, IO direct addressing mode. This mode can be used only to access 64 standard IO registers, which are located at the IO addresses 0 to 63. So this addressing mode cannot be used with, for example, if you want to say LDS instruction, so you cannot, the LDS instruction cannot use this addressing mode. Or if you want to use the IO registers which are in the extended IO address, then this addressing mode cannot be used. So here is an example. So if you say out address comma rs, so you are basically saying put the value of register rs into the IO register whose address is given. So for example, here you are saying read the value from R16 and put it in the IO register whose IO address is 0x20. And similarly, uh, here you are saying like read the value from the IO register whose address is 0x19 and put it in the R19 register. Remember, the difference from the direct addressing mode, the difference of IO direct addressing mode from the direct addressing mode is that direct addressing mode is used to can be used to access any memory location. Again, direct addressing mode can be used to access any data memory location. Doesn't matter if that location is within the range of IO standard IO address registers or not, right? However, IO direct addressing mode, this can be used only if the register from where you want to read or the register to whom you want to write, they are in the range of the standard IO registers. So this is how the instruction code will look like. You will have an opcode. You will have I don't know how many bits you can do the math. So if like I if I think you are allowed to use 16 to 31 registers, right? So if you are allowed to use 16 to 31 registers, so from 6 to 6, 7, 8, 9. So these bits are used to specify your register, for example, R19 or R16, and 6 bits they will be used to specify they will be used to specify the address of the IO register. Again, remember that the AVR microcontroller has standard 64 standard registers. And if you have 6 bits, you can address 64, you can make 64 different combinations, right? Or you can address 64 locations, right? So that's why this addressing mode can be used only with the standard 64 standard IO register, because you have only 6 bits in the instruction code to specify a register. The registers which are in the extended which are extended IO registers, they have their address greater than 64. So that's why you cannot use these instructions like out and in, for example, with the registers of ADC like ADMUX or ADC SRA and so on, right? Any questions? Okay, then let's go to our next quiz. Okay, go ahead and try this one, quiz 4. Okay, I can give you 30 more seconds. Okay, so first question, select instructions that use two register addressing mode. So the only instruction that uses two register addressing mode is add R16 and R17, right? And second question, select instructions that use direct addressing mode, right? So direct addressing mode, there is only one instruction which is using direct addressing mode, and that one is LDS, or load from static memory, R16, comma 0xF0F0. If you think that my answer is not correct, then let me know, we can discuss, right? Uh, Third question, select instructions that use IO direct addressing mode, right? So there is only one instruction which uses it, and that is the last one in R17, comma pin B. Okay, so let's go to the next addressing mode, which is register indirect addressing mode, right? So a register, in this case, a register is used as a pointer to the data memory location. So uh, so how many of you know, like, is there anyone who doesn't know what is a pointer? You can write in your chat box, in the chat box. Anyone who doesn't know what is a pointer? Pointer to memory location. Okay, it seems everyone knows what a pointer is, so I don't need to explain. Okay. So a register is used as a pointer to the data memory location, and one of the three 16-bit registers can be used as pointers. So so this is how like it looks like. So you put a value in the register, and that register can be X, Y, or Z register, right? You put the value in that register, and then the value is used to point to the memory location, and from that memory location you actually read or write data. Okay, so and the register X, it is basically combination of R26 and R27, Y is combination of 28 29 register, and Z is combination of R30 and R31, right? And so X, Y, and Z, those are basically 32-bit register. Why 32-bit register? Because the the address range or the size of the memory is big enough, and it such is big enough so that it cannot be all of the locations cannot be addressed using an 8-bit register. So we need combination of two 8-bit registers to make X, Y, and Z. Okay, and actually you can also, since X is a 32-bit register, you can also access the low and high byte of that register individually. So for example, if in an instruction you say XL, so it is equivalent of saying R26. If you say XH, it is equivalent of saying R27, and so on. And it is also shown here in the figure. X high is R27, X low is R26, ZH is R31, ZL is R30. Okay. So for example, if you write the instruction, so this is load. Okay, this is not load static, it is load, only load. So load here, when you say load X R24X, so it's basically you are saying that whatever address is available in the, whatever value is available in the register X, use it as go to that location in memory, and from that location put the value into R24. So for example, if I'm saying X is equal to 10, right? I'm just making up some number. So here, this is our register X, right? And here you have value 10. So then the microcontroller will go to the address in memory at location 10. And let's say this is your location 10 here, address is 10. And let's say the value in the address is, I don't know, let's say 100. Okay. So the value in this address is 100. So this 100 will be placed into R24. So R20, after the execution of instruction, R24 will become equal to 100. It will contain the value of 100. Okay. Same is true when you say load R19 comma Y. So you are saying, okay, go to the address which is pointed to by a value of register Y and read the value from that location or that address and put it in R19. And same here in Z. So the complementary instruction is store instruction, right? So again, the thing is same here. For example, when you say store X comma R18, so you are saying read the get the value of R18 and store it in the memory which is pointed by the value of the register X. So for example, uh, again, let's say if X is equal to 10, right? And the value of R10 is R18 is, let's say, 20, right? So what will happen, that since the value of X is equal to 10, microcontroller will go to the memory location 10, which contains 100 currently. But after the execution of this instruction, store R18X, what will happen? This will be overwritten and it will contain new value of 20. Okay. And same goes here. The only difference is that now Y will be used as a pointer, not X. Okay. Any questions? Okay. If no questions, then we have our next quiz, which is quiz 5. Okay, go ahead and do this. Okay, so let me stop here. So this is incorrect. Why is incorrect? Because the second instruction in the code snippet is wrong, is incorrect. Why? Because it says store R29, R17. But with the store instruction, you must specify, if you are saying ST, you must specify the address of the memory either using X, Y, or Z register. You cannot use an 8-bit register like R29 to specify the location of the memory. Okay. Okay, should we do this example? Okay, let's try doing this example. Okay. So write a program to copy the value of 55 into the memory locations 140 to 144, right? So first we are because we need to write the value into five memory location like 140, 141, 142, 143, 144. So we are going to run a loop. So we are putting the value of 5 as a loop counter in register R19, right? And then we are loading in R16 the value which we want to write in in those five memory location, which is 0x55. So we are simply saying load 55 into register R16, right? And then uh, we are actually let's stop here because I don't want to rush over the example. Uh, we can do this example next time. You have 2 minutes before your quiz is released. Do you have any questions? Any questions? No? Oh, quiz is not released in last 50 minutes. It is released in last 10 minutes. So I have some time. So let me do this example then. So initially, we are putting 5 in R19 as a loop counter, loop variable, loop counter. Then we are putting in R16 0x55, which is the value we want to put into these five memory location 140 to 144. And then we need to load the address, starting address. What is the starting address? Like address of the first location where we want to put our value. So the first address is 140. So what we are doing, we are going to load it in, we can load it in one of the those 16-bit register, either in X, Y, or Z. So let's say we select Y. So in Y low, we put the low byte of the address, which is 40. So we are saying load immediate, put in YL 0x40, right? So we are putting low byte of the address in Y low, and then in Y high, Y low is and in Y high we are putting the high byte of the address, which is 1, right? So load the low byte of Y with the value 0x40 and load the high byte of Y with value 0x1. You can actually also write it in a more readable form by saying load immediate YL comma low 0x140. So you are basically using the directive, right? So it will again do this exactly the same thing. So you will put 0x40 into YL, and you can also use high directive here. So it will put 0x1 in YH register, right? And then what we are doing, we are saying, okay, now put the value of R16. What is R16? 0x55. Where in the memory location pointed by Y. What does the Y have? Y have this memory address 0x140, right? And then we are simply incrementing the pointer. Again, this is important. You can increment you cannot increment Y register. Okay, but you can increment the low byte of the register. Okay, so if you say increment YL, what will happen? The address will change from 0x140 to 0x141. Now it will be pointing to the next byte, right? So it is like this. So you have, so here you have 140. This is address 140, then address 141, and this is address 142. I'm not writing all of them, but you have already put here, you are saying put R16 into 140. So here you placed 55, right? And then you said increment YL. So when you say increment YL, so YL was what, 40, so it become 41. So the total address, 32-bit address will become 141, right? And now you are decrementing R19, which is just your loop counter, and you are checking if it is equal to 0. If not, then go back to the loop, to the label L1, right? And on the label, now you are saying, okay, put R16 in Y. Now Y is what? So Y is, remember, Y is combination of Y low and high. So Y high was 0, 1, and Y low was incremented. So Y is pointing to this location here. So you are saying now put value of 55 into this next location, right? And then you are saying, okay, now increment YL. So it will become 0142, right? And now you are saying, okay, decrement R19 just to check if you need to stop looping or not yet. So you go back. Again, you are saying put R16 in Y. So it will place 55 here. Okay. And so on. I don't want to iterate it 5 times, but what will happen that every time you are incrementing the pointer, and the address will be same, data will be copied in all 5 locations of the data memory. Any questions? So this is different from direct addressing mode. Let's say if, what does I mean? So if, let's say if I don't use ST instruction and I use STS. So if I use STS instruction, what I need to specify? I need to specify the address. I cannot specify a register like 0x140, comma R16, right? So I cannot run a loop because now I cannot change this number. So what I need to do every time, I need to write this instruction again. Everything same, and here 141, right? And R16, and then STS 142, comma R16, then STS 143, comma R16, and so on, right? So I cannot dynamically change this address if I'm using the direct addressing mode in STS instruction. But if I'm using the register indirect addressing mode, as in the store instruction, I can dynamically change the address which is contained in the Y register. Just by changing the value of the Y register, I can change the address where the data will be stored. Okay. So again, any questions? If not, then that's it for now. Your quiz will be released in 1 minute or in less than 1 minute. So go ahead and do it, and I will be available online until the end of the lecture time.